we go. Okay. So we should see a little record button in the top left-hand portion of the Zoom screen. And with that, I will hand over the proceedings to Group 13 and let them share their design with us.
All right, well, hello everyone. Thank you for coming out to see our presentation. We're Group 13, and our bioreactor is called BIOS, the Biological Incubation and Operating System. Beginning off this presentation, I'm going to go over an overview of generally how our product works and how a user would operate it to begin the autonomous operation. Additionally, after that, I'll dive into a subsystem math covering each part of our subsystem and how it meets various needs. And lastly, we'll wrap it up with a cost comparison between our three models and any questions anyone has to ask. When designing BIOS, we decided to focus on modularity. So currently with our deluxe model, our bioreactor can manage 3 independent experiments at the same time. However, with a focus on modularity, clients can choose between 1 to 3 chambers for their bioreactor. Here is an open view of our overall bioreactor. The outside is removed, so you cannot see the doors or the shell. Some important things to note here are on the left side, we have our well plate manipulation apparatus. This holds our liquid and fluid dispensing as well as our FI and OD sensors. On the bottom right, you can see it pointing to our testing chambers. There are 3 of them here that you can see. Other important details are the elements of our heating and cooling, which we have our heat vent and our heating and cooling water reservoirs in the back, as well as our fume hood adapter to allow our device to work with a BSL-2 biosafety cabinet. If a user was beginning to start up this device to begin using it, all they would have to do is choose which reactor they were going to use, place their well plate or test tube holder inside, lock it down with the thumb screw, and then also put in their desired filter into our FI sensor and fill up the liquids in the front with the desired cleaning solutions and whatever liquids they desire in the reactor. And then the reactor can begin processing once you activate it on our touch screen on the front. Here is a close-up of our testing chamber by itself. It has 3 main important elements inside of it. One is our mixing element that of course covers the 3 orbital patterns, one being linear, orbital, and double orbital. We have our gas dispensing solenoid at the bottom and our heating and cooling radiators. The only one that can be visible at this time is the cooling radiator on the right side. One last important thing to note about the testing chamber is, of course, the door opens automatically using a motor in a series with the gear visible on the right to open and close the lid, and it is sealed with a refrigerator magnet seal. Here's a close-up of our well plate manipulation apparatus. This holds our fluid management pipette, our waste management pipette, and our FI and OD sensors. And of course, all of this is attached to our 3-dimensional Cartesian gantry. On the left side are some important time calculations in regards to how long it will take to fill up a well plate with one liquid, how long does a tip exchange take, and how long it takes to perform operations of the FI and OD sensors.
So in order for the machine to effectively dispense both the fluids for the cell culture and the waste, there is a rack as seen in the photo here that contains 3 bins and 6 glass beakers, and it's located right in front of the testing chambers. So overall, there are the tips for the fluids all the way on the left, the tips for the waste are right next to it, and then there's the trash for all the tips on the right of them. So the bins for the tips are strategically placed, and their placement allows the tips to be attached on the respective pipette without interfering with the other. These bins can be purchased on OpenTron's website, and they hold 96 tips at a time. The tips are polypropylene, and each tip is held in an individual compartment. We then have these 6 glass beakers on the right, and they are where all the fluids needed for the process will go. From left to right, we have the dirty bleach, in which the waste management will put the cell cultures in to neutralize after the experiment is over, and the clean bleach, which will be used to rinse out the pipette, as well as the water to rinse out after using the clean bleach. The 3 beakers to the right are then designated for the fluids that we will need for the cell culture.
Right, so the first subsystem we're going to review is the main structure. The dimensions are given as shown, 0.9 meters by 0.9 meters by 1.2 meters. We chose a 1-inch 6061 aluminum square tubing to make the overall frame. It'll be welded together. We also have supports in the rear for the heating and cooling subsystems. And we plan on using 1/16 inch polystyrene plastic to cover the exterior, and those bolts you see on the front are to fasten it to the frame. We chose polystyrene because we wanted to reduce the overall weight and help it withstand, the high temperatures that may be created by heating and cooling. And polystyrene is also non-toxic and often used in lab settings. In the rear, we have 320 millimeter fans that assist in venting out waste gases at the end of each experiment. And then as you can see on the front, we have our emergency shutoff in case of accidents. And then we also have our display hooked up right there. We plan on using a Raspberry Pi to handle all processes and power the display. And we also use plastic to reduce the overall weight of the bioreactor. We found out that the main structure effectively weighs half the weight of the bioreactor, so we can separate the main structure from other internal subassemblies, so it is easier to carry.
Right, so the second element is the mixing element. It consists of a slider crank, orbital shaker, and holder. The slider crank attributes to linear motion, and the orbital shaker attributes to rotational motion. There is a NEMA 17 motor for both the slider crank and orbital shaker, each reaching 500 RPM at a high load on the mechanism. At the very bottom of the mechanism is the slider crank. Slider crank moves a guide rail carriage on which the orbital shaker is attached to. The orbital shaker has 4 offset orbital shafts for stability of the holder that rotates above it. The holder has a slit where the well plate and conical tube slide into, and a thumb screw that is used to clamp them into the holder. Below the holder is an LED array for the OD sensor that will be discussed later. So here are the dynamics for the mixing element. On the left is a diagram of the slider crank, and in the middle is a diagram for the orbital shaker. Beneath them are the dynamic equations that relate the motor torque as the input state and acceleration as an internal state. The velocity of the mixing element is an output state and is determined from these values. On the right is a side profile of the mixing element. These equations allow for the user the ability to adjust the motor torque to reach a desired speed in RPM. So large possible deflections in the mixing element during operation could yield to catastrophic results in the whole mechanism. The guide rail was identified as a high-risk part because it is long and thin compared to the rest of the parts. A single beam analysis is shown. The mixing element exhibits a torque on the guide rail at its maximum acceleration is determined using the dynamic equations from the previous slide. R is the distance from the center of mass to the guide rail, and M is the maximum mass above the guide rail. Using the torque generated on the beam along with the maximum weight, the deflection at the worst case is 5.1 micrometers, which we deem as negligible.
So the liquid handling and sensor systems access the well plates or conical tubes via our dispenser movement system. The system is comprised of a gantry similar to that of a CNC machine, where the system is mounted on the frame of the main structure and is suspended above the workspace, where it is capable of producing movement in the 3 Cartesian axes of motion. Each axis is driven by a NEMA 17 stepper motor that is coupled to a lead screw, which threads into a slider that is free to move one-dimensionally along the guide rail. At the end of each guide rail is a limit switch that the slider will contact to determine the homing position of the dispenser. Since the motor rotates in discrete steps, the positioning resolution was found by converting the step size to a linear dimension. The threaded rods used have a pitch of 24 threads per inch, and a NEMA stepper motor has a step angle of 1.8 degrees. Converting the step angle to linear motion using the pitch of the lead screw produces a positioning resolution of about 0.00529 millimeters for each axis of motion. Using the same method of converting angular motion to linear motion, the maximum travel speed was found for the motor. The maximum load for the NEMA motor is 6.12 kilograms, which produces a maximum linear speed of 30 millimeters per second. Using the no load speed for the motor, which was 183 millimeters per second, the maximum speed in each direction was determined using interpolation. These speeds were later used to find the various dispensing times that were previously mentioned. The deflection of the guide rail in the X direction was determined to account for positioning accuracy in the Z direction. The guide rail was modeled as a cantilever beam with a constant cross section that is fixed at both ends. The bending moment induced on the beam by the weight of the Z-axis guide rail is maximum when it is placed at the center of the beam. The bending moment was then used to find the bending stress at this location, which then provided the strain in the beam using Young's modulus of the beam's material. Strain is defined as the ratio between the deformation and the original length of the beam. This relationship provides us a deflection of only 1/100th of a millimeter. This deflection is very small and can be considered negligible since it is less than the positioning resolution.
Next subassembly is the gas dispensing system. For this, we're going to be using a series of solenoids. They're 1/8 inch in diameter. Here is a quick calculation for the flow through into the testing chamber. We assumed a minimum pressure inside the tubes coming from the lab of 4.3 PSI, following through with some head loss, and it came to a fill time of about 36 seconds. Located down at the bottom corner of this image, you can see the inlets that the user will plug in the tubing into. These behind this inside the testing chamber is the solenoids, which will flow into the testing chamber. This is a top-down view coming from the outside connectors in the bottom corner. It'll flow into each individual chamber to the inlet solenoids on the inside of the individual chambers. When an experiment is done, the testing chamber roof will open and the fans inside will start to spin, as well as the fans on the main structure. And it'll vent from this hood at the very top of the structure into a bio cabinet.
Our next subsystem is our heating and cooling system, which is responsible for temperature regulation. We have implemented a liquid-based heating and cooling system, which allows us to reach the desired temperature ranges outlined by the customer within the required time. 2 liquid reservoirs are located on the back of BIOS, one for hot fluid and one for cold. For the cold fluid, we are using a combination of 70% water and 30% glycerin. This is to reduce the freezing temperature to around -9 degrees Celsius. Water is used for the hot fluid. A series of pipes and pumps are used to distribute the fluid to the testing chambers, where radiators are used to circulate air and distribute heat. A 600-watt submersible heating coil has been placed in the hot water reservoir, which is used for heating the water to the desired temperature of 90 degrees. For cooling, we have designed a unique apparatus consisting of Peltier plates, water cooling blocks, and a CPU cooler to vent off additional heat from the thermoelectric. Before any experiment can be run using BIOS, customers must prime the temperature regulation system. To prime the system, the reservoirs must be filled with liquid as the pumps are ran at a low power. This will flush liquid throughout the pipes while also filling the reservoirs. Once the system is full of fluid, users will enable the heating and cooling units. Pictured here, we have calculated the total time needed for the fluids to reach the necessary operating temperatures. For the hot reservoir, this is 90 degrees, and for the cold, this is -4 degrees. At this point, the 2-liter reservoir will be fully filled and the fluid will begin at room temperature. The heating coil will be operated at the full power of 600 watts for priming, and the maximum power of our cooling unit is about 70 watts. Considering all of these factors, it will take about 16 minutes to heat the hot reservoir and 48 minutes to cool the cold reservoir.
In order to determine the power loss through the walls of the testing chamber, we did a 3-dimensional analysis. For this, we had to calculate the shape factors of the walls as well as the edges and the corners. Doing this came out to a heat loss at the maximum temperature of 75.7 watts and at a heat transfer into the chamber in the cold situation of 28.4 watts. This is a brief view at how the piping actually works. Starting in the top corner with the reservoir labeled H, the water will flow out into the pump. It will be pushed through the radiator inside the testing chamber, where a fan will force convection over the fins. The water will lose some heat, return back to the reservoir to be reheated by the submersible heater. Similarly, with the cold reservoir, the water will flow out through a pump into the radiator inside the testing chamber and then be returned to the reservoir. However, we don't chill the water inside the reservoir. This will have to be pushed out to a different cooling section of our energy system, and it'll be pushed through the coolers. We'll cover this briefly later. This is a top-down view of how all the pipes actually fit together. Starting with the cold, there's the blue pipes which flow into the testing chamber and then are returned to the green. For the heating, they flow out through the red and return through the yellow. And then the bottom left corner, that's where the chilling happens. The white is the out and the blue is the return, or the black is the return. This is a see-through picture of how the heating coil fits into the reservoir. It's inserted to the bottom, and we'll be using it at max power when priming the system, and then it'll be throttled down depending on how much heat we're using to the system. In order to handle the high temperature water, we've had to consider using a hot temperature pump as opposed to the ones used for the cold water. And then the desired temperature of the fluid inside is to be 90 degrees. For the cooling, we'll be using the thermoelectrics. Pictured on the far right is the cooling stack. This is the entire system of how we cool the water. Starting from the bottom is insulation. Up from that is an aluminum block, which allows water to flow through it to transfer the heat to. Up from that, there's the thermoelectric, which pushes the heat into the heat sink up at the top, which is CPU cooler, which then exchanges the heat with the atmosphere. Each cooling stack has a cooling power of about 35 watts, and we're trying to get the temperature down to around -4 degrees. In order to do this and prevent water from freezing, we'll have to have a 70-30% glycerin water mixture, and that'll bring the freezing temperature down to -4 or -9.4. And then the total power of the system that we need to vent through the CPU cooler is 115.5 watts, and the cooler is rated for 120 watts.
An important consideration is the external temperature of BIOS. While the testing chamber will be inside the main structure, the reservoirs will be external. As such, we made sure that the temperature of these reservoirs will be safe to touch by heavily insulating them. A thermal resistance network was set up on the reservoir to determine the necessary insulation thickness while minimizing the heat lost through the walls. This is what's pictured on the right of this slide. The temperature outside the wall was set to 20 degrees, which will be safe to touch. The temperature at the internal wall was assumed to be the temperatures of the liquid inside of them. The reservoirs are made of aluminum, which has a thermal conductivity of 205 watts per meter Kelvin. We have selected polystyrene as the insulation material, which has a thermal conductivity of 0.04 watts per meters Kelvin. The area used was the largest area on the reservoir, which will have the lowest resistance and therefore the greatest heat lost. All of these values are pictured on the left of this slide. We performed an iterative process to determine the necessary insulation thickness. After performing multiple trials, the insulation thickness was decided to be 15 millimeters. Calculations are shown on the right for the heat rate for both reservoirs. Using this 15 millimeter insulation thickness, the heat lost from the hot reservoir is about 1.19 watts, and the rate of heat transfer to the cold reservoir is about 0.4 watts. The heat loss from the hot reservoir is over the desired 1 watt. However, this was deemed acceptable to ensure a nominal dimension for the insulation.
So for the fluid management system, we are using a linear actuated pipette made by Opentrons. This is the P300 model. Some important calculations for the system include that the Reynolds number is 604.7, the flow rate is 300 microliters per second, and the accuracy and precision are 0.6% and 0.3% as taken from the website. The achievable volume is 5 microliters to 20,000 microliters, and this achievable volume is taking into account the pipette returning to the reservoir. Then for the waste management, we're also using a linear actuated pipette made by Opentrons. However, this model is the P1000. A larger pipette was chosen for this model since accuracy and precision aren't as crucial as they are for the fluid management system. And some important calculations for the system include that the Reynolds number is 604.7, the removal rate is 1,000 microliters per second, and the accuracy and precision taken from the website are 0.7 and 0.15%. The fluid and waste management system both have auto tip ejection functions, allowing for the tips to be removed of and placed in the waste bin quickly. Also, both the fluid and waste management are attached to the gantry that was shown in the dispenser element, and a mount made out of ABS is used to attach both of them to the gantry.
BIOS is equipped with a sensor element subsystem that is responsible for taking spectrometry readings. Our customers require that BIOS be able to take measurements for both fluorescence intensity and optical density. For this, we have implemented 2 assemblies within this subsystem, one for each measurement type. First, we'll present our fluorescence intensity apparatus. Our fluorescence intensity apparatus consists of 3 main components. All of these components will be enclosed in ABS 3D printed structures, which will then mount to the gantry. The first and most important component is the photomultiplier module, otherwise known as the PMT module, created by Hamamatsu. PMT modules are highly sensitive pieces of equipment that will convert light into electrical signals. A circuit is built into the PMT module that will output any readings as a current, which can then be wired back to our main controller. Our PMT module has a spectral range of 300 to 740 nanometers, which can therefore measure all light within the visible range. Additionally, our PMT module has a settling time of 0.2 seconds, which means the FI sensor assembly can take an accurate reading of a well within 0.2 seconds and ensures BIOS can measure fluorescence intensity within the customer desired time of 6.5 minutes. In fact, the FI sensors of BIOS can process a 384 well plate in 1.58 minutes, as stated earlier. The next component for the FI assembly is a microscope filter cube from Thorlabs. Emission filters can be inserted into the filter cube, which will filter light to a specific wavelength as desired by the customer. Over 100 fluorophores are compatible with the Thorlabs filter cube set. Users must input the desired emission and excitation filters into the filter cube before an experiment is performed. A dichroic mirror must also be placed inside the filter cube. This mirror will first direct the input light straight down towards the sample. Once the light impacts the sample will emit a specific fluorophore. The light from this fluorophore will come back straight up through the dichroic mirror where it will impact the PMT module for readings. The final component of this assembly is a 1-inch 1.5 watt mini LED. This LED is the light source for taking FI readings only. This source will output the light that passes through the mirror as stated previously. An important concern was raised about whether the light source would be powerful enough, and we have taken steps to ensure that it is efficient. The power of the light source output is set by the maximum measurable power of the sensor. Our specific PMT module has a cathode radiant sensitivity of 189 milliamps per watts. This is essentially how much current the PMT can convert per unit watt. Additionally, our PMT can only output 2 microamps of current at maximum. Considering both of these equipment properties, we deduced that the PMT module can only measure about 0.01 milliwatts as pictured to the right. Therefore, our light source will be more than powerful and in fact will need to be throttled down. This is not surprising as PMT modules are a very sensitive piece of equipment. PMT modules are specialized for low sensitivity measurements, meaning they are designed to work with low level light detection scenarios.
As for the optical density sensor, the sensor assembly consists of the following parts. First, a 918D SL-OD 3R photodiode made out of silicon inside an ABS 3D printed structure. The photodetector is compatible with DB15-based Newport that then will be connected to a Raspberry Pi. The light source consists of a LED source located below the well plate in the mixing element, whereas the OD sensor will be attached to the dispenser. So the light passes to the well plate and is received by the optical density sensor. The optical density sensor can read 600 nanometers and has a spectral range of 200 to 1100 nanometers, which also measures the desired wavelength. The light source can output 600 nanometers as well. And finally, the maximum measurable power is of 2000 milliwatts. And now, for the power consumption, I would like to mention that the following data is analyzed when the experiment with the 3 testing chambers is taking place at the same time with the 3 motors. So that is the worst case scenario. So the power usage by the total system, and again, in the worst case scenario would be 600 watts by heating and cooling, 120 watts for dispenser moving in 3 axes, and 240 watts for the 3 mixing elements. So by adding up the power by every subsystem, we get a total usage of 960 watts. Again, in the worst case scenario, which is below the 1000 watts by the power supply maximum output.
All right, So our cost breakdown depends on which model the customer is purchasing. Our first model is our basic model, which consists of one chamber, which is about $9,500. We calculated that each additional chamber would cost about $470. So our standard model consists of 2 chambers and our deluxe model consists of 3 chambers. As for a cost breakdown of our 3-chamber model, our deluxe model, we found that 3/4 of the cost came from OTS parts, and then the final quarter of the cost came from raw materials, manufacturing, assembly labor, and energy consumption. Now we're going to explain a little bit of why you should choose BIOS over the competition. Well, our main benefit is our unifying goal, which is our modularity. We can maintain 3 different gas compositions, temperatures, and dispensing fluids, which means we can run 3 individual experiments. Each subsystem was designed to be separable from each other in the main assembly for easier transportation. It's also very efficient at heating and cooling, and all processes are entirely automated. All that is required is setup before the experiment and a little cleaning after experiments. We also have many precautions against cross-contamination, and we know that we are below the budget for our 2-chamber models. Additionally, our 1-chamber model is even $500 below budget. And our fume hood adapter allows the bioreactor to sit next to a fume hood in a lab, and waste gases will exit BIOS through the fume hood adapter. This concludes our presentation. Thank you for your time. Do you have any questions?
Okay. Well done. You guys are fast. You've got 20 minutes to go on the countdown timer, so we'll have a little bit of time to let you interact with the panel. So, any immediate questions from our colleagues on the panel?
Hey guys, this is Tom Singer from Northrop Grumman. I mentioned to Rick Miles off on the side, this is the second presentation in a row where we had structures analysis with shear moment diagrams. Good work. I would much rather see that than see a FEM. I hope I haven't like traumatized anybody with my FEM feedback, but this was much better. It's the right tool to use for the problem you're trying to solve. That said, could you flip back? I think the second set of shear moment diagrams that you had with the double cantilever beam. Yep, that was it. Yeah. This is a double cantilever beam, right?
It's one singular cantilever beam fixed at both ends.
So double cantilever beam. It's like fixed in all degrees of freedom at 2 ends of the beam, right? All right, correct. Double cantilever beam. All right, that fixed constraint, does that apply a rotational constraint as well?
Yeah, it's so at both ends of this specific cross beam, it's bolted into the sliders that are on the 2 guide rails on either side.
So preventing it from rotating at either end?
Correct.
Okay, so what's wrong with your shear moment diagram?
There should be moments at either end.
Yeah, it should be non-zero there.
Correct.
This is a statically indeterminate structure, and I was mentioning to Rick, they're a pain in the ass. So right, so you've got to I don't know if Dr. Traum typed that in response to me just now. Yeah, so you've got to like figure out what your moment is at each end, and there are various ways you can do that. A real simple way to do that is just make it not statically indeterminate, so that you know exactly where your moment is. But yeah, that's something to be corrected here. But otherwise, I mean, I definitely appreciate the tools that you brought to bear on this problem. Let's see. At the very beginning of the presentation, you kind of went over the actions that a user would be taking to start the system in terms of what consumables they're providing and loading into the machine, which is good. But what would really help out is sort of the next step. What is the machine going to do after the user says go, right? So what process is it going to do? What's that going to look like? That's going to help reviewers and customers understand what your capabilities are and what capabilities might not be there. So that's something that would be very helpful to kind of show, whether that's as an animation or whether that's just you kind of walking through, the various steps of, oh, we're going to put fluid over here, and then we're going to take some fluid out of here, we're going to dump it over here, we're going to dispense a pipette tip, we're going to shake things, we're going to put caps on, all that sort of stuff. As a walkthrough up at the the very front, or even probably better at the front than at the back, but at some point just to kind of communicate that information would be very helpful. Your hot water tank, right? So you're heating up water to use as to deliver heat to your samples.
Correct.
Yes.
And you said that's sitting at 90 degrees Celsius on a tank on the back of the machine, right?
Yes.
And you said it's insulated, and your insulation is enough to keep it at 20 degrees Celsius on the outside. Is that correct?
Yes.
That's correct.
How is your insulation keeping the outside of a hot tank colder than room temperature?
20 degrees Celsius. We believe that is that not room temperature that we used?
Is that? Well,
we believe that
okay,
is room
so
temperature.
It's keeping it at room temperature,
yes,
right? So
that is correct.
So you, with 1.5 centimeters of polystyrene, you're keeping no sensible heat or temperature through the system with 90-degree water on the inside.
That is what our calculations led to. Correct.
Interesting. That's I guess 20 is room temperature. That's very effective insulation. Let's see. Your power budget. I appreciate you putting that up, because I don't think any other teams have covered that. So I definitely appreciate you putting that up. It seems like it's missing, and I certainly recognize that not everything is going to be operating at the same time, but you're not covering the power for your optical sensing system. You're not covering any power needs for a user interface, and I know that nobody's really talking about user interfaces because that's mostly software and hasn't been done at this point, but it is going to have some mechanical aspects in terms of power draw. Startup of pumps could be an issue, which obviously can be solved with a few capacitors, but those sorts of things. So I don't know that it's necessarily a true statement that your worst case is 960 watts. But that said, that that would be a worst case calculation, and it's probably going to be easily under 1,000 watts when you look at realistic analysis. And there's one other thing. Oh yeah, you're on your. I apologize, I'm jumping back and forth in your presentation. Your closed boxes, right? You've got a lid on the box that's held down, you said, with magnets.
It's not held down by magnets. It's held down by its own weight.
Yeah. Well,
the magnet is just
with magnets, I guess. Yeah.
Yes.
What kind of torque is it going to take to open that at the hinge?
The torque required is, excuse me. The torque, it's 0.331 Newton meters, and we have 1.26 Newton meters power from the motor, including the gear.
Okay. All right. Yeah, that's a. I mean, obviously, if you're trying to open a door, you want to do it not at the hinge, but if you're able to do that with your motors, then that's great. And I guess the last question I'd have is, I don't know if you covered the frequency that you're shaking your shake table at.
Yeah, so it's going at 500 RPM, which is
okay. So something like 8 or 9 hertz or so.
Yeah.
Have you looked at any vibration analysis to identify if there's anything going on in your system that you know, an 8 or 9 hertz excitation frequency could excite?
So we didn't do any vibrations analysis, and that was because since this whole mixing element is surrounded by the 10 millimeter thick of styrofoam of the chamber, lots of those vibrations are going to be dampened out. And we didn't see any members that would be excited by any low frequency vibrations.
Okay.
So this is Rick Miles, Northrop Grumman. So I think one of the things that would have been helpful in this presentation is just tying it to the requirements, kind of along the same lines of walking through what it's supposed to do. Right, I had a tough time picturing the clear advantage of the 3 modules and why I would want to buy a 3 module system over a 1 module system. I just couldn't picture. I mean, I'm looking at the, if you go up to the beginning of your presentation where you're showing the overall apparatus, yeah, that right there. So I'm having a tough time picturing what's going on in each one of those modules. Is it just a different well plate, different tubes? And therefore, if I decide to take one of them out, I've still got the same outside enclosure, right? So if I buy the 1 module system, right, I've got a lot of wasted space, or am I not understanding it correctly?
Yes, you're understanding it correctly. If you would just remove each of those modules in those testing chamber modules if you wanted the lower cost model.
Okay.
Additionally, the primary benefit to the multiple chambers is each chamber will have its own heating, its own gas concentration, and its own mixing with its own well plate, its own fluid. It is designed so that you can run 3 separate experiments. That is the main reason it exists.
Okay, and I guess that's what I was kind of getting at with the requirements. So I'm still trying to understand what is required by the customer versus what is like a nice to have, right? Did the customer require the ability to do multiple experiments, or are they focused on doing 1 experiment at a time? And I've been watching all these presentations, right? Y'all are the last one. I still don't quite gather exactly what the overall need is from how many experiments they would like to perform at one time.
From the customer needs statement, they were relatively vague about that. However, there was the subtle hint at for something like the heating where it says it needs to individually heat and the specific well plate, and same with the gas, it needs to create an individual environment per well plate, but there was no specific where it says you need to have more than 1. That was just something we kind of went with, and then gave the option of you can have it if you desire to have the 3, or you can just go with the 1 if you need be.
And it kind of ties
Okay.
into our job concept a little, where we wanted to really, you know, branch out with modularity, and we still wanted to, you know, keep it under budget. So we found out that, yeah, we were able to, you know, do more experiments while still being under budget, and that still, you know, helps out our modularity and it's more benefit to the customer.
Okay, and then your heating and cooling, right? So the time to heat the hot water has been that seems to be pretty consistent with what I've seen on other groups, but the time to cool your cold water seemed to take an awful long time compared to what I've seen elsewhere. So I was curious as to why your system seems to perform differently than I've seen in others. So
we were using this this plot in the middle here as a reference guide as to how the cooling power actually works with the thermoelectrics. A good average, essentially you sacrifice cooling power for differential in temperature. And in order for us to actually attain the correct differential in temperature we're looking for, we had to sacrifice the cooling power, which is something I believe a lot of the groups decided to leave out for the sake of convenience. So it's a little bit harder for us. However, we have the correct data. And again, these are only as good as the the manufacturers say they are. So we have an additional, our purchase order has an additional 5 of these. There is some data on being able to stack these to increase the cooling power or the temperature differential. So a lot of this will come down to prototyping and testing phase.
Okay, thank you.
Thank you.
Okay.
Questions before another Northrop Grumman person came on.
Oh, sorry. Somebody asking? I heard a slight.
Joel, can you speak up a little bit?
Yeah, how's that? Is that better?
There we go. Yep.
Okay. Yeah, I was going to let someone from Cummins jump in here since we had 2 people from Northrop Grumman, and I'll be a third if I ask them questions, but I don't see them on right now. So let me go ahead and ask the question. So I had the question about the cooling also. It seemed like a long time for that. When you guys size the dirty bleach beaker, try to say that 3 times fast, did you put any consideration to, how did you size that? The same size, I think, as every other beaker, right?
Right. It was just we wanted a uniformity of height, and also we wanted it to fit within a small space. So it was kind of just trying to fit the best of both worlds. And given that that beaker size its diameter is about the size of the syringe buckets we will be receiving from the Opentrons, or as our clients would have to buy, and also the height is very similar. Thus, it would make the programming of the location of that easier for that phase of making the product.
Okay, so that's a possible trade-off you might want to look at, because it might end up being the limiting factor to how many experiments you can run. Let's see what else here. I was looking at the mixing element, and maybe it's just because of the diagram. Does it only have support on one side, or is it supported on both sides?
It has
support on both sides.
Sorry, Mikhail.
Yeah.
You can go and go.
Yeah, all good. Yeah, there's a support on both sides of the guide rail.
Okay, but then it looks like it's uneven. It looks like it's more toward the left and back.
It's kind of like it's on a monorail.
Yeah, it's a little bit offset. That's dependent on the heating and cooling system, because the fans are. So if we were going back to here, yeah. So the motor has to be a little bit further from the fan, so that's why it's a little bit offset.
Okay, so if you go to a slide right after the mixing element, maybe that's not the one where you showed the deflection of the rail that holds
yeah, right there. So the deflection,
okay.
I wanted to do at the worst case. So in case, during production, say we could have had the mixing element in the middle. I wanted to do the deflection at the middle, because that would yield the most deflection. So that's why I did the analysis there.
Okay.
Yeah.
All right. Thanks.
Thank you.
Kind of following up on that. If you go back, I mean, this thing is basically sitting on a monorail, more or less.
Yeah.
What are lateral acceleration? Because I mean, in an orbital pattern, right? This thing's going to be going side to side. I'm waving my finger like you guys can see me because I don't have a camera on me. What's that going to do laterally and twisting wise to that beam?
So we did the calculations with the acceleration at its maximum, and we didn't. There wasn't much deflections with the from the side to side. It was mostly with the back and forth along the rail.
Yeah, I wouldn't expect side to side to necessarily be a huge deal, but I would expect torsion to be maybe a concern, and if not from deflection, then potentially from wear, because it's really just it's only contacting at a limited location there. And you can imagine the whole thing is going to kind of want to wobble, right? So it seems like that's maybe not the most structurally sound way to do that.
Yeah, well, that's why we did the the deflection, at least vertically up and down, was I think 5.1 micrometers, and we didn't
up and down isn't such a big deal, right? Because you're not accelerating up and down. You're shaking side to side.
Right.
So that's kind of the bigger deal there.
Okay, I got you.
And if I could go back when Rick was asking about the requirements that we're driving 3 separate chambers, I forget which one you mentioned that the requirements from the customer were kind of vague, and you sort of you intuited a requirement from them. Customers often write vague requirements, and you can get yourself into a significant amount of trouble if you go trying to guess what the customer meant when they're not clear. So it's always a good idea to be in contact with them, and where you think something's not obvious. We talked with the last group where they're very specific about we want a 1.2 factor of safety. Well, 1.2 factor of safety, in a structures world is nothing, right? So probably that's not what the customer meant, right? If NASA's launching rockets with 1.5 factors of safety and they have to be super light and go through all sorts of controls to make sure that materials are what they think they are, you probably, 1.2 is probably way too sporty for, something that's going to sit on a bench top in a lab, right? So customer probably wrote the wrong requirement there. And it sounds like if you're, trying to get inside their head and what did they mean, way better just go ask them, hey, what did you mean? Right. So be in contact with your customer, especially in a situation like this where you do have such a very well-defined customer who's writing requirements for you.
At the beginning of the semester, we did have a interview that was provided to us with our customers. And as I don't know if you know, there are many, and each of them had their own idea of how many experiments they wish to run. Some will only care about 1, some want up to 6. That is why we wanted to create the multiple options so that we could try to please multiple. And that is where the vagueness sort of came in. We wanted to appease as many as possible with that interaction we had at the beginning.
Okay.
All right. Any more questions from our panel, or Mike Fitzgerald or Brooke even? No. Okay. Well, so you guys are the last group. So I don't know if you know this, but there's a tradition in 4501 that was started about a year ago where the last group gets to answer an incredibly challenging fundamental thermo question, which is if one of your thermo instructors asks you to calculate the amount of entropy that your system generated in the laboratory environment that surrounds the system, how would you guys do that calculation? That question gets asked every semester at the very end, and I don't think anybody's aware of it until they're the last group. So how would you guys calculate the entropy generated by this system?
Anybody got it?
You seem to have caught us unaware, Dr. Trom.
It catches everybody unaware. Interestingly, in the very, very beginning of class, when we did the thermo review, there's a page on Canvas that gives you the answer, but you would have to know where to look. So I'll give you another second and then I'll help you.
Are we a closed system?
Man, I'm glad it's you guys and not the panel that has to answer this.
I remember the slide. Is it the one with his grave on it?
Boltzmann's grave. No, it's although that's a good way of thinking about most thermo questions. That's yeah. My wife pointed that out to me. She's like, why do you love thermodynamics so much? Like all the heroes of thermo all died really young. Carnot, Boltzmann, like all those guys died in their 30s or 20s. It's like, yeah, well, that's kind of the way of the nature of the discipline. So it tends to drive people crazy a little bit. So And the reason, by the way, that I asked this question is because this was a final exam question that I asked when I was a brand new assistant professor at the University of North Texas. We taught a thermo class where we actually walked the students through the university's central plant. And it turns out that there is a dial in the, and I'm not sure that the same is true at UF, because I think UF has multiple cogen plants spread all over the place, but UNT is a smaller physical campus. There's one dial that actually was, if you knew how to read it correctly, you could track the entropy generated by the entire university campus. And so that was my final exam question. So imagine sitting down for your thermo final, having one question, which is what's the entropy generated by your university? So I was not a very popular thermo instructor. That's why they don't let me teach it here. But so yeah, so Drew got a good start with closed system, right? So is it an open or a closed system? And one way of modeling it makes the answer much easier than the other.
I hope it's a closed system. I would think that usually makes it easier.
There you go. Okay. Yep. Closed system.
And it's been quite a minute since I've taken thermo, but if we're a closed system, do we generate entropy to the surroundings or?
Yeah. So there's gonna, if your system is the envelope of the environment, then yes, you're going to be in general reducing the entropy inside the environment, right? You're increasing the order inside the environment, and the universe has to respond with a corresponding decrease in order, all other things being equal. And entropy is a little bit, I used to, this is another reason they don't let me teach thermal. I used to describe entropy as being like rabbits. It's unlike energy, which at least for us as mechanical engineers is conserved. Entropy tends to multiply, right? So if you get a little entropy in a little corner somewhere, like, putting two rabbits in a cage, that there's more and more by 2 weeks, you've got a whole cage full of rabbits, and entropy is the same way. So if you've got a little bit of entropy somewhere, it tends to kind of grow. So it's not conserved. But what's the only way that entropy can cross the system boundary for a closed system? Uh-oh.
Like temperature?
Okay, yeah, that's part of it. So maybe even more fundamentally, what's the difference between a work transfer process and a heat transfer process?
Work transfer and heat transfer. It's no, that's not correct.
They both carry energy across the system boundary.
Right.
What about entropy?
It's only temperature.
I believe only heat does entropy. Is that correct?
Yep. That's it. Yeah. And that's nobody ever teach. And it's not just a UF thing. Nobody teaches that in any thermo class that I've ever sat in. No professor has ever said, except for me, but that's why they don't let me teach thermo. The difference between a work transfer process and a heat transfer process is work transfer is energy transfer alone, and heat transfer is carries energy and entropy across the system boundary. So I think you guys have got all the pieces now. Somebody said temperature. I think it was Jonathan or maybe Ricardo said temperature, and then Drew's got the heat part of it.
Well, I believe since the heat we are venting off would be the heat from our heat vent, I'm leaning towards that being a factor. That's where our temperature is distributed from the reactor.
Okay, good. All the pieces. And then what are the units of entropy?
Entropy is in is it in joules?
Am
I off
no,
here?
That's energy.
It's energy. Oh man.
Joules divided by Kelvin.
There you go.
Thanks.
Perfect. Okay. So you've got the heat in joules. You've got the temperature in Kelvin. The ratio is Q over T.
Q over T, we're giving off.
So entropy is equal to the work divided by the temperature.
Almost the heat output divided by the temperature. Because remember, heat transfer carries entropy, work transfer does not. So how would you guys do it? I think you have a sense of how much heat your system is rejecting. And I think you know the temperature at which that heat's being rejected, right?
20 degrees Celsius room temperature. That's the external temperature, not the temperature of the heat vent itself.
Yeah, no, you want the temperature of the heat vent. You want the temperature at which the heat is actually moving across the system boundary. So those are two values you can measure, right? Heat and temperature. So the total entropy that this thing is rejecting to the environment is just that Q over that T.
Okay.
That's coming from a lot of sources.
We have our thermoelectrics transferring, and then all of that. We got the
heat fans, the heating coil, the power supply, the
testing chambers.
Yeah.
Testing chamber.
We got a lot of heat going out.
It's a lot of thermistors.
But it's amazing, right? It's incredibly simple when you at the end of the day, it's really just that heat that you're rejecting over the temperature, and all those different things that are generating entropy and heating things and cooling things and all of that stuff, all that entropy that lives inside the system boundary, all just gets collected and dumped out of that heat vent, and that entropy transfer rate is Q over T. So at the university, the answer to the final question, by the way, at UNT, is that they had a cooling tower basically, and so the water, you guys might not have taken John Abbott's class yet, but if you do, there's a cooling tower lab in there. So the gauge was a gauge that measured the amount of makeup water. So the rate at which makeup water was being reintroduced into the cooling tower. And so from that rate of makeup water, you could figure out what the evaporation rate was. And if you knew the temperature at which the evaporation was happening and how much water was leaving the system, latent heat of vaporization divided by the temperature at which it was happening, that's the entropy rejected by the whole university. So you guys have got a miniature version of the same system.
Guess we're just gonna buy one of those then.
Buy one? No, you've got everything you need right here. So anyway, sorry to hit you guys with that question, but it's become a tradition. So I had to ask. The first time I asked it, Scott Banks emailed me. He was the interim chair at the time. He emailed me afterwards, and he's like, "That was the single greatest question anybody's ever asked in a 4501 final presentation." So anyway, sorry it had to be you guys, but I have to ask it every time.
It's okay.
An enlightening experience.
Yeah.
Brooke didn't warn us about this.
I don't think Brooke. Yeah, no. It's only the last group knows. So now you guys get to keep the secret. And then the thing that's even more fun is so alumni of the class get invited back. I don't no, you guys probably missed it. Benny Lagoy was in here for a little while. He's an alum of the class and also a former TA. Well, so what I was saying is alumni get invited back. So if you guys, when you graduate and you get the invitation from the alumni office to come back, know that you could come into that last meeting and of the capstone sequence. It'll happen in the summer too. So you guys might even still be around. You can come into that last meeting and see what happens when we ask the last question to the group that goes last about how much entropy their system rejects. So anyway, fun little Easter egg that very few people know about in 4501. That's why they don't let me teach thermo. Anyway. Okay, I think we're done. Sorry, we ran over with my little thermo question. So we'll call it there. But thanks for sharing your design with us.